Hi everyone, my name is Sila and come from witthayalai school. Today I would like to present you in the topic of RSA data encryption. This is my presentation outline. Cryptography is an indispensable tool for protecting information in computer systems. Like when A wants to send secret message to B, the cryptography will help you to protecting data and your information. Cryptography is used in many applications like banking transaction cards, computer passwords, and e-commerce transactions. There are many types of cryptography, but I choose RSA encryption because it is well known and it is very easy to understand. In cryptography, RSA is an encryption that uses public key cryptography. What is public key cryptography? Public key cryptography is a cryptographic system that uses pairs of keys. There are public keys, which may be disseminated widely, and private keys, which are known only to the owner. The RSA algorithm was the world's first public key encryption algorithm. The acronym RSA is made of the initial letters of the surname of Ronald West, Adi Sharma, and Leonard Adleman, who first publicly described the algorithm in 1977. The security of RSA is based on the difficulty of finding prime factors of large integers, because it is very hard to find prime factors of large integers. So, my objective is to learn about RSA algorithm and write a computer program for this algorithm. Before you learn RSA algorithm, you must know some basic concept of number theory that you will use in RSA algorithm. The first one is the very basic. It is the greatest common divisor. The greatest common divisor of two integers a and b will be denoted by GCD of a and b. Next one is modulo operation. It said, let a belong to integers and n belong to positive integers. A modulo n is the remainder of division of a by n. For example, 5 mod 2 equals 1, 40 mod 7 equals 5. Next one is congruence. It said, let n be a positive integers and a b belong to integers. Then, a congruence b modulo n when a minus b divisible by n, and a not congruence b modulo n when a minus b not divisible by n. For example, 42 congruence 23 modulo 19, and 20 not congruence 11 modulo 2. And the last one is Euler free function. Euler free function, or we call it phi n, is the number of non-negative integers less than n that are relatively prime to n. For example, phi 4 equals 2 because 1 and 3 are relative prime with 4. Phi 5 equals 4 because 1, 2, 3, and 4 are relative prime with 5. Euler free function properties. The first one is said, if p is a prime number, then phi p equals p minus 1. And the second one is said, if p, q are prime numbers, then phi of pq equals phi p times phi q equals p minus 1 times q minus 1. For example, phi 13 equals 12, and phi 91 is equal to phi of 7 times 13. It is equal to phi 7 times phi 13. So it is equal to 72. Now I'm going to talk about RSA algorithm. Suppose Alice wishes to enable anyone to send her secret message, which only she can decrypt it. First, she will pick two large prime number p and q, and then she will compute n equals p times q. Then she will compute phi n. We can find phi n is equal to p minus 1 times q minus 1, because n is made of prime number p times prime number q. Then she will choose an encryption exponent e, which satisfies GCD of e and p minus 1 times q minus 1 equals 1. And now, Alice's public key is the pair of n and e. Then she will apply the extended Euclidean algorithm to obtain an encryption exponent d, which satisfies e times d congruence 1 modulo p minus 1 times q minus 1. Suppose Bob wants to encrypt a message to Alice. First, he will look Alice's public key and represent his message as an integer n, which is strictly less than the public modulus n. The ciphertext is then produced by raising the message to the power of the public encryption exponent e modulo public modulus n. We can write it in equation as c equals m to the power of e modulo n. Alice on receive the ciphertext. She will decrypt the ciphertext to recover a message. By exponentiating by the private decryption exponent d, we can write it in equation as m equals c to the power of d modulo n. Okay, for example, Bob want to send secret message to Alice. First, Alice will choose two big prime numbers p and q, and then she will compute n equals p times q, and also she will compute phi n. And then she will choose an equation exponent e equals 23. She can use e equals 23 because GCD of phi n and 20p equals 1. And now, Alice's public key is the pair of n and 23. Then she will obtain a decryption exponent d equal this because 23 times d is congruent 1 modulo p minus 1 times q minus 1. Now, Bob represents his message as 50. To encrypt a message to Alice, he will use this equation. C equals m to the power of e modulo n. The message that he wants to send equals 50. So, 50 to the power of 23 modulo n. I compute it already. The ciphertext is equal this. And then Alice, on receiving the ciphertext, she will decrypt the ciphertext to recover a message. She will use this equation. M equals c to the power of d modulo n. The ciphertext that she received to the power of the public encryption exponent d modulo n. So m equals 50. Let me see the message that Bob wants to send to Alice and the message that Alice received from Bob equals 50. Is it the same? And it is my RSA code programming that I have written in my algorithm. I use Microsoft Visual Studio 2010 to make this program. According to the situation in the example, you must key prime number p and q, and the program will compute n and phi n. Then you must choose public encryption exponent e, and the program will compute into the private decryption exponent d. The next one is encryption and decryption method. First, you must key the message that you want to send, and the program will compute into the ciphertext. And in decryption method, you must key the ciphertext that you receive, and the program will compute into the message. Let me see, the message that you want to send and the message that you receive after you decrypt it is the same, so this program can work. But if we use prime number p and q that have many digits like 5, 6 or more than that digits, the program will take a long time to compute all the process. So, my future work is to develop the algorithm to make the program can work better when we have prime number p and q that have many digits, and to make the program that can compute from the plain text into the ciphertext and can decrypt the ciphertext into a plain text. Thank you for Assistant Professor Dr. Kisada Sampanan, Department of Mathematics, Faculty of Science, Chiang Mai University, Upala Witthayalai School, DPST and IPST. Thank you.